Hello to you from Chem Help ASAP. This video covers the challenge of drawing chair conformations and determining the stability of different chair conformations. Check the video description to find links to printable copies of these problems and their solutions. There will also be links during the video that will connect you to other relevant tutorial videos. Okay, before we get into the problems, let's look at the idea of a chair. So in the upper left, I've drawn a cyclohexane. Cyclohexanes have a special conformation, and that conformation is called a chair. Now, why would we call it a chair? Let's draw a chair toward the middle of the screen. That is a chair, or it's meant to be a chair. You might say that looks like no chair that I've ever seen. Well, let's add some artwork to this and see if we can't make it a little more clear. So that is supposed to represent a person sitting in the chair. We have on the right hand side, this is the headrest, and on the left we have the footrest, and here in the middle area we have the seat of the chair. I can't take credit for this fancy artwork. This was first shown to me by Professor Paul Noshel, who was my instructor at the University of Michigan in fall in 1991. Professor Noshel is now in Germany, but anyway, he drew that on the board. I think on the last day of class he drew that picture. But it does illustrate the idea of how this could be perceived as a chair. Now, on the bottom of the screen, let's redraw our chair. Let's try to draw this kind of big. So that's one chair form. The interesting thing about chairs is they have different conformations and they flip. So let's, and these aren't connected, they should be connected. So let's number our atoms. And now let's redraw our chair flip. That's still the same shape, but the chair looks like it's just turned around. Well, it hasn't turned around. This carbon has kind of bent downward, and carbon 4 has bent upward, and the seat of the chair has kind of changed. But this still, on the far right, that is still carbon 1, 2, 3, 4, 5, 6. The carbons haven't rotated. It's just that we've kind of refolded the shape of this molecule. Now, let's look at carbon 1. Carbon 1 is interesting, not for the ring atoms so much, but the groups on carbon 1. And so for cyclohexane, we'd have two hydrogens. The top hydrogen, since it points straight up and down, we call this an axial group. And the other hydrogen, which is more oriented within the plane of the molecule, is an equatorial hydrogen. As it turns out, our axial hydrogen is pointed up from the ring. The equatorial position is therefore down. And you may say, that doesn't look very down, it's only barely down. Well, every carbon has an up group and a down group. The axial is definitely up, so the equatorial is definitely down. Let's go to carbon 4. And there's our axial and equatorial positions. Note that in this case, the axial is definitely pointed down from the ring, and the equatorial hydrogen, therefore, even though it lies roughly within the plane of the molecule, is definitely up. So every carbon has an up and down position. Now when we flip these, carbon 1 on the far right still has an equatorial and an axial group, an up and down group. Now this hydrogen is equatorial, kind of lies within the plane of the structure. It is still up, and here this one's clearly down. This is axial down. Now, just to be clear, if we put a star label on that axial up hydrogen on the left, it is still up, but now it's equatorial. So when you flip a chair, groups go from being axial to equatorial. But note, the up hydrogen on the left is still the up hydrogen on the right. It just goes from axial to equatorial. So kind of a common thing you'll see when you look at chair conformations is you want to see where your groups are, the axial or equatorial, and we want our larger groups to be in equatorial positions because just sterically there's more space for groups in the equatorial position rather than in the axial position. So this is kind of the mindset we'll take as we go and do these problems. We're going to look at different chair conformations and try to see which one is more stable. Problem number 1. So here is our structure in the upper left. This is a cyclohexane. It has a single methyl group on it. Let's go ahead and number our carbons for reference. And let's draw our first chair. I tend to always draw this chair first. That's just what I naturally tend to draw. Note that this chair is not perfect. These are kind of squiggly lines. The chair just has to be good enough for you to get information from it or to communicate to other people with your what you're trying to represent. So let's number our atoms in the ring. So we need a methyl group off carbon 1. I am going to arbitrarily say that the carbon, this methyl group, off of number 1 is up in this chair, and the hydrogen is down. So this is axial and up, and this hydrogen is equatorial, and down. This chair is in equilibrium with another chair conformation. Let's draw that chair. Did a little better job on that chair. Let's again number our carbons. Note that carbon 1 is on the far right in our left-hand structure. In our flipped chair, it's also going to be to the right. So now carbon 1, it has two groups off of it. One is going to be axial down. The other is equatorial up. The up group is still going to be the methyl group. So this is our CH3. This is now equatorial. Still up. And now the hydrogen, which was down, is still down, but it's axial down instead of equatorial down. So here are our two chair representations. There's nothing of note on the other atoms. I typically don't require students to put in the hydrogens off atoms that don't have other substituents, but there are hydrogens there, and we could draw them in if we really wanted to. As always, follow the instructions of your instructor. Your instructor doesn't care what Chem Help ASAP taught you. What your instructor cares about is what your instructor taught you. So follow your instructor's lead. So for these two structures, the more stable structure, it would be the one that puts the larger groups in the equatorial position. So our methyl group is in the equatorial position on the right. This is the more stable chair. Problem number 2, in the upper left we have a di-substituted cyclohexane. We have 1, 2 methyl groups. Let's, as usual, go ahead and number our atoms in the ring to give us reference points. Now, going down to the main part of the screen, let's draw our chairs. Number these as well. Perfect. Now, on position 1, our picture shows that methyl group being up. So that is our up group coming off of the ring. There's our methyl. The other bond on carbon 1 is a hydrogen. So this is an axial up methyl and an equatorial down hydrogen. Now let's look at our next substituent. That's carbon number 3. Carbon number 3 should also have a methyl group up. And there's our methyl group pointing up. Notice that the two bonds to carbon 3 both kind of make an arrow pointing up, so the axial group, the vertical group, will also point up. Equatorial is that hydrogen. It still lies within kind of the plane of the ring. So that is equatorial. There's axial. Great. Now, let's draw our flipped form. Not perfect, but workable. So 1, 2, 3, that's all we need. But we will do the rest. Now, on carbon 1, the the hydrogen was equatorial down. It's still down, but now it is axial down. And the methyl group is up, but up has an equatorial orientation. Great, now let's go to carbon 3. Carbon 3, the hydrogen equatorial down is now going to be axial down as we go to the right-hand conformation. And the methyl group, still up, but it's now equatorial up versus axial up. So these are our two chair conformations. Which one is more stable? Well, the structure on the right puts the methyl groups in equatorial positions, and therefore the right-hand structure is more stable. Problem number 3. Again, we have a di-substituted cyclohexane. Now they're not the same substituent. One's an isopropyl and one is a methyl. It's a different orientation. Instead of 1,3 di-substituted, it's 1,4 di-substituted. But let's go ahead and go through the same process. Let's draw our cyclohexane ring. Let's number our atoms. So on carbon 1, it says that group is up. The up group will be axial up. There's our isopropyl. And in the equatorial position, we'll have that hydrogen to finish out carbon 1. Now we could put groups, hydrogens, around all the positions in the ring. I tend to leave them out because it makes the picture look messy, but no mistake, they are certainly there. Our next substituted carbon is carbon 4. Now, that methyl group is up. I'm going to draw the axial position first. The axial position is down. So the up group is equatorial. Again, kind of pointed off within the plane of the ring. Now let's draw our flip of this. Again, 1, we won't number them all, but 1, 2, 3, 4. Off of 1, now the axial position, what was down in the left-hand structure was equatorial, but in the right-hand structure, down will be axial. So it's axial down, and the equatorial will be our, I almost said methyl group. It's not a methyl group, it is an isopropyl group. Now let's go over to carbon 4. Carbon 4 has as its two substituents a methyl and a hydrogen. The methyl, which was equatorial, will now be axial, still up. And the hydrogen in the left-hand structure was axial down. It's still down, but now it is equatorial down. Okay, so we've drawn our conformations. Which one is more stable? We'll note that both of them have something in the axial position. In the right-hand structure, we put the methyl axial. In the left-hand structure, we put the isopropyl group axial. The isopropyl is bigger, and so the strain introduced by putting the larger group axial is worse than having a methyl group axial. So the structure on the right is more stable. We try to put our bigger groups equatorial, even at the cost of putting something axial, at least where our bigger group gets its preference of being equatorial. So the right-hand structure is more stable. So problem number 4, again, we have a di-substituted ring. Now we have groups in the, they're 1, 3 relative to each other, but I'm going to number the ring in the same direction that I've been numbering the other rings, just to show a little bit different perspective. It won't make a difference, but I just want to be consistent in how I approach these structures. So on the left, towards the bottom of the screen, let's draw our first chair, and let's be inconsistent and do this a little bit differently. Let's draw the other chair on the screen at the same time. So there's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Great. Okay, so we have both chairs. Now we just need to drop in our substituents. So for carbon 1, the methyl group is up. That happens to be this axial position, and the hydrogen is equatorial. And change it up again. Let's go over to carbon 1 now in the other chair conformation, and let's take care of carbon 1 in both structures first. So the methyl group is up. It is still up, but it's not going to be straight up because the hydrogen is now axial down, and so when the methyl group is up, it's equatorial up. Okay, so that's carbon 1 all taken care of. Now let's take care of carbon 5. Carbon 5, the methyl group is down, which means that the hydrogen is up. So up on carbon 5 would be that hydrogen. And so that means down, and that's axial. So that means the ethyl group is down and equatorial. Down and equatorial off these middle carbons is oriented a little bit like that. Perfect. Okay, let's go to carbon 5 on the right-hand structure. Now again, so the bonds to carbon 5 both point down. So the down position for this structure is going to be axial down. So the ethyl group goes from being equatorial down on the left to axial down on the right. And that means the hydrogen, which was axial up on the left, is now equatorial up. Okay, so great. Those are our two chair conformations. Which one is more stable? Well, note in the right-hand structure, we put our bigger group, the ethyl, in the axial position. That's a bad idea for sterics. So the the left-hand structure is actually the more stable because we put our larger group, the ethyl, in the equatorial position. That doesn't always work, but in general, unless you're looking at less common substitution patterns, you always want to put your larger group equatorial if at all possible. Okay, we're going to wrap it up with problem number 5, and it's a little bit different. Instead of giving us a structure, it gives us a name. So this is trans 1,4-dimethyl cyclohexane. So in the upper left, let's draw our cyclohexane, number our positions, and now let's see, trans 1,4-dimethyl cyclohexane. Now we could either make the methyl groups up or down. I'm going to make them. I'm going to choose to put the first methyl group up. So carbon 1, there is our up CH3. That means when we go to our methyl group in the 4 position, it has to be down. So that's our starting structure. Pretty often these kinds of problems, when they want you to draw chair conformations, they'll give you a name, expect you to draw the molecule, and then create your own conformation pictures. So that's where we start. Let's draw our chair. 1, 2, 3, 4. That's really all we need. Now on carbon 1, that methyl group is up, and up on carbon 1 is axial up. Let's go over to carbon number 4. For carbon number 4, we have a methyl group down, and down on carbon 4 is actually axial down. Now when we draw our flipped form, 1, 2, 3, 4. Always keep track of your atoms. On carbon 1, the down position is axial, and that will be the hydrogen. That'll now be axial. And the up position is equatorial. And there's our methyl, which of course is up, and it is still up. Because up and down don't change, but axial and equatorial do. Now as we go to the left, we have the up position on carbon 4 is now the hydrogen, which is now axial, and the down position is our methyl group, which is equatorial. So those are our two chair conformations for this molecule. Now let's figure out which one's better. As I look on the left, I see these axial methyl, axial methyl. Those are typically not very favorable, so the more stable conformation is the structure that we've drawn on the right. So there are 5 problems that deal with stability of cyclohexane structures. I hope you found this video helpful. Please subscribe, like, or leave a comment or question. Thank you for watching. Remember that links to these problem sets are in the description. Take care.